Hi, good evening all. So we will start with our session. So from today onwards, we are starting our sessions on steel structure design, wherein we are going to cover warehouse design, then connection design, what are the shear connections and movement connections, then anchor bolt design. Anchor bolt will just go through the preliminary design or preliminary information. Then we'll have gantry girder design, then base plate design. So there are few sessions which are there. So we'll go one by one. So from today on, today we will start with the warehouse design. So all of you must have seen the warehouse somewhere. It's like a shed type structure. Uh, it can be used for storage or where or like a garage or some maintenance locations. So in that case, there may be some time we have a gantry girder over it or crane just to lift the heavy equipment in case of fabrication store. So this is the basic purpose of shed, just to cover or enclose the space so that we can do some work beneath it. So we'll just go through the design basis for the warehouse. We'll just start with the one of the example. So this is the one of the example we are going to consider. So we are considering that location of shed will be in Pune. So why we need a location of the structure? Because we need to get wind load data and seismic loading data for that particular location. So we need is the location where the structure is going to be erected. Then basic size of the shed, what is required. So this size can be derived from the architectural drawing. In architectural drawing, mostly the total length and width of the structure is mentioned. Along with that, whether it is cladded structure or open structure or partially cladded or partially open structure, whether it is having any gantry girder or just shade for covering. So all those details are present in the architectural drawing. So to get those details, we have to refer architectural drawing. Here in this design example, we have considered the height of the structure 9 meter, width of the structure 12 meter, and length of the structure is 30 meter. And we are not considering any future expansion, either horizontal or vertical. So this is one of the cross section of this warehouse or structure. So here in this case, you can see this is the actual our steel members. These are the cladding runners where we can fit this cladding. So you can see this is one of the channel section which is connected through this plate to the column, and sheeting is supported on that channels. So these are called as cladding runners. The same arrangement is there, but it on the roof. So we have here same channels. Those are fixed with the rafter by clit angle, and over those channels, sheeting is provided. So we call it as a purlin over which sheet is supported. So purlin spacing will be governed by the spacing spanning of the sheet. Spanning of the sheet means this sheet has some span. This sheet is provided by, or it is a vendor item. It is readily available in the market, and based on the loading capacity, its span is defined by the manufacturer. So most of the time, the span of the sheet is around 1.2 to 1.4 meter, based on its thickness and load carrying capacity. So that we can find it on manufacturer's catalog. So these are the two columns along the width, and this is the top beam which is connecting between two columns. So this is called a rafter beam. or a rafter, right? These are the foundations. We have some wall on the outer side so that water should not get entered into the shade. Sometimes we have some bracket over here in order to support the gantry gutter. When we want to lift, or if it is a maintenance shed where we want to lift some pump or heavy equipment, during that case, normally we provide gantry girder inside the shed, which lifts the heavy object during maintenance. So this is the plan view. This is the plan view of the structure. So total length is 30 meter, which is divided into 6 span, 5 meter each, and in transverse direction, the total span is 12 meter. So we have two column intermediate. So these columns are called as gable end columns. So these two ends, the end on grid 8 and grid 1, these are the gable ends, and we have column on both the ends. So these columns help us to run the cladding runner, or to shorten the span of the cladding runner on both the faces, so that we can span the cladding runner between these two columns to support the sheeting. Okay. So when we are planning for this structure, we have to check the span and its height, so that we can have proper bracing arrangement, so that the angle should not get exceed more than 45 degree. Okay. So we'll go through this design basis, then we will go through the how to calculate wind on this shade, what is internal pressure, what is external pressure, how wind is calculated. So we'll go one by one. So these are the foundation data. This is typical like borehole and what type of soil it is, what is founding depth we have considered, how much is the tape bearing capacity, is there any water table, or all these values are, you can get it from any geotechnical report. Whenever you work on any project, there will be a geotechnical report from where you can get all this data. Then superstructure is of steel frame. Lateral load resisting system will consist of steel column fixed at base and steel bracing system. So normally here in this case we have considered fixed base, but it is always advisable to consider the pin base column. Pin base column. So does anyone have any idea why we have to consider the pin base? Anyone? What if we consider fixed base, and what will happen if we consider pin base? Anyone? So when pin fixed base is considered, what fixity creates? When we have a fixed beam, what it creates?
Moment.
Yes, it will create a movement. So if these are the beams, if these are the fixed beam, then it will create a movement, maybe like this, for this load. Okay. So whenever there will be a fixity, then there will be a movement, and we want to design the connection, because when we are providing shade, the shade is supported on the concrete pedestal, and the force whatever getting developed in those columns, that will be transferred to the pedestal through anchor bolts and base plate. So whenever there will be a movement connection, or movement is there due to the fixity, then that movement has to transfer to the concrete pedestal through the bolts. So if the movement is very high, because shed is almost like a cantilever structure, it do not have any bracing in the transverse direction. It has bracing in longitudinal direction, but it cannot have bracing in transverse direction. We cannot have bracing here because the length and span will not be able to meet, or the section size required will be huge. So we are not able to keep it pin in this direction. So when we create a fixity here for top frame, in that case we can consider pin base here. So once we consider pin base, then movement will get reduced, and our anchor bolt base plate, it will be designed only for the compression, right? So always keep in mind, not only for the warehouse but for any structure, steel structure, whenever we are going for the base plate connection, as much as possible it should be a pin base connection instead of um, fixed base connection. So fixed base connection, one, it creates a problem of number of anchor bolts required are huge, and size of anchor bolts required will be heavy. Then in order to fit all those number of anchor bolts, we need to increase the pedestal size. So ultimately the size of the pedestal will get increased too much, and just because of that increased pedestal size, the clear dimension or clear space which is required for the warehouse, that will also get reduced. So this is why we avoid fixed base connection for any structure. Then what is design criteria here? So we are following the IS 875 part 1 for the loading. So these are the loads, height of wall. These loads are calculated to get the load on the foundation, not on the structure, because all these self-weight of brick, then internal plaster, all these are supported directly on the grade, not on the structure. So if you can see, it will be supported on the grade level, at this level. So all the load will be transferred directly to the soil. This is the loading on the working floor, means the loading on the grade floor, that is 1.2 kilonewton per meter square, and that will be transferred to the soil directly. So loads on the roof. So this load will be acting on the shade or roof. So the sheet thickness here we considered 0.6 mm thick galvanum sheet, and its self weight is 0.15 kilonewton per meter square. Okay. So this is provided by the manufacturer. They have different kinds of sheets and different thicknesses of sheets. So we have to refer this catalog, and from that we can get the load of that sheet. Then these are the densities of the materials, like steel having 78.5, plain concrete PCC it is 24, then reinforced concrete it is 25, brickwork 20, water 10, cement plaster 20, and soil 21. So now what are the live loads? Live load on the roof is around, as per our code, we have to calculate it based on the how much slope we are having to our roof. So if slope is greater than 10 degree, then we have to reduce the live load by 0.02 kilonewton per meter square for every increase in the slope over 10 degree. So if roof is inaccessible, if we are not able to access that roof, then live load is 0.75 kilonewton per meter square. So in our case, or in our this design example, our slope is 14 degree. So it is more 4 degree more than the 10. So what we are saying, that as the slope of roof is greater than 10 degree, reduce the live load by 0.02 kilonewton per meter square for every increase in the slope over 10 degree. So over 10 degree, there is 4 degree extra slope. So for that 4 degree, we have to reduce this live load. So 0.75 minus 0.02, this is the reduction in live load into 4. 4 stands for this difference in degrees. So actual live load will be 0.67 kilonewton per meter square. And this load will be applied either on the purlin if we are modeling it or directly on the rafter. So we'll see in the STAD how we have to apply all these loads. Then wind load. So this is one of the most important part of any warehouse, because normally warehouse is not having sufficient dead load to take care of any uplift due to the wind or seismic. So this load has to be calculated accurately, because this is the most governing load in any design for warehouse or any uh, structure, because structure weight or steel structure is having its self weight is comparatively less as compared to the concrete structure. So wind load and seismic loads are most of the time governing load combinations in case of the steel structure. So here we will calculate the wind load as per IS 875 part 3. So basic wind speed, this is VB, it is 39 meter per second. So we get it from this code. In code, it has given for the different areas or different cities. So for Pune, we have selected it is 39 meter per second. Then risk coefficient K1, this is probable mean designed for 50 years. So it is the probability factor. So we'll go here in the code. So this is K1. It is based on the 50 years mean return period. So based on the study of the wind over the 50, 100 years, they have just given this factor K1. Then terrain height or structure size factor K2. K2 is 0.88. How we have to arrive at K2? We'll see from here. So terrain height and structure size factor. So from this name, what we can conclude that this K2 factor depends on terrain or the area where the structure is located, and height of the height and structure size, its vertical height compared to its horizontal dimensions, both directions horizontal factor. So based on all these three parameters, the factor K2 is worked out. So first is terrain. So selection of terrain category shall be made with due regard to effect of obstructions. So what we have to see while selecting the terrain category, the obstruction, how much obstructions is there surrounding the structure. If more number of obstructions, then the wind load will be less, because it will get shielding effect or it will get shielded from the other structure. So if structure if the terrain is open, then K2 factor is less. If terrain if if terrain is open, the K2 factor will be more, and if it is crowded or it is surrounded by many structures, then K2 factor will be less. So there are 4 categories based on which we have to select the factor K2. So first category defines exposed open terrain with few or no obstructions, and in which the average height of any object surrounding the structure is less than 1.5 meter. So this category 1 is for the exposed terrain where it is completely open, like you can say a desert, where it is completely open, there is no obstruction, or if anything is there, then it will not be more than 1.5 meter. Then we can call it as a category 1. Then category 2 is open terrain with well scattered obstruction having heights generally between 1.5 to 10 meter. This is for the some terrain where we have very limited structures or limited obstructions, like in the village, where we have uh, homes separated more than 10-meter, 20-meter. So that can be considered as category 2. Category 3 is terrain with numerously closed space obstructions having the size of the building or structures up to 10-meter in height with or without or few isolated tall structures. So this category we can consider somewhere where like a, city area, not a metro cities, but just some of the cities like Nasik you can consider, like Nagpur, where there are structures closely spaced, and its height is up to 10-meter. So this can be considered as category 3. And category 4 is terrain with numerous large, high, closely spaced obstructions. So where we have a high-rise structure or tall towers, like if you see the Mumbai area where we have all the high-rise buildings spaced close to each other. So that case we have to consider category 4. So based on this, we have to consider the category. We have to analyze what kind of area is there, what are the obstructions, what are its height. Based on this, we have to select the category. Then next is based on the size and height and size of the structure. So based on that, we have 3 classes: class A, class B, class C. So what this class A denotes, when the structure or their components such as cladding, glazing, roofing, etc. having less maximum dimension means greatest of horizontal or vertical dimension less than 20-meter. So if any structure or their components, anything total, like total extent of cladding, sometimes we may have some architectural cantilevers. So all those, if those are less than 20-meter in any direction, then we can consider it as a class A. For class B, the same components, if those are between the 20 to 50-meter, this is the range for class B. If those dimensions are between 20 and 50-meter, then we consider it as a class B type. And class C is the structure where one of the component, either horizontal or vertical, anyone, if it is greater than 50-meter, then it will be a class C. So based on this, we can get the factor K2. So two conditions are there. First, we have to find the terrain category, and second thing, we have to find the class of the structure. So based on this, we have K2 factor is given in the code here. So if we are considering K2 structure in Pune, so it is closely spaced structures or buildings. So we can consider the terrain category 3. And class, since our structure width is 9-meter by 30-meter by 12-meter. So 30-meter is the longitudinal length, 9-meter is the height, and 12-meter is the width. So we are just between the 20 to 50-meter. That is class B. So terrain category 3, class B. So this will be my coefficient for the K2 factor. And structure, our height of the structure is 9 meters. So it is given for this height is 10 meter. So corresponding to this 10 meter, we will consider K2 factor is 0.88. So from this, we will get the factor K2. So we got the 0.88. So clear this, how we got this K2 factor. If any doubt is there, just stop me and ask me.
सर
हाँ.
सर वो आप कैटेगरी सेकंड में था 20 बिटवीन टू 50 मीटर, बट इसमें जो डायमेंशन दिया सर 12 into 30 मीटर दिया है,
Right.
सर इसका ब्रीथ लेंथ तो 30 मीटर है, विड्थ इसका तो 12 मीटर है, तो इसको
Yes.
कैटेगरी 2 में कैसे डाल रही हूँ?
Right. So what we discussed, any of the horizontal or vertical dimension. Greatest of horizontal or vertical dimension. If it is less than 20, then it is class B. If the greatest of horizontal or vertical dimension between 20 and 50, then we have to consider class B. So what is our greatest dimension?
30-meter length.
50 meter. So it is falling between 20 and 50. So that's why we are considering class B.
Okay, sir.
So we got the factor K2 0.88. Any doubt in this? So we'll move to the next factor, factor K3. So third factor is topography factor. We'll see it here. So topography means, it is simple. Its word itself denotes topography means how is the nature of the ground. So it is a completely flat ground. If it is valley or it is cliff or mountain area. So based on that, this K3 factor is mentioned. And in most of the case, this factor or the effect of topography will be significant at a site when the upwind slope is greater than 3 degree, about 3 degree, and below that the value of K3 may be taken as equal to 1. So when the slope of the ground is 3 degree, then we have to derive this factor based on interpolation. If it is less than 3 degree, then we have to consider it as a 1. Okay, so based on this, we consider topography factor is K3 because we consider that our land is completely flat, or it is not that much steep. So this topography factor we considered as 1. So what will be the design wind velocity? It will be a design wind velocity will be basic wind speed into this our probability factor into this terrain category factor, and this one is K3 is the topography factor. So once we multiply all these factors, we will get the design wind velocity. It is, we are getting it 34.32 meter per second. So this is just the velocity, not the pressure. So once we got the velocity, we have to calculate the wind pressure. So wind pressure is given by 0.6 into Vz square. So these formulas are there in the code. So this Pz is 0.6 into Vz square. So this is design pressure. So we got design pressure of 706.717 Newton per meter square. This is Newton per meter square. Keep in mind, it is not in kilonewton per meter square or kg per meter square. It is Newton per meter square. Okay. Then slope of the roof, we have 14 degree. So as per code, whenever we are considering wind or seismic load, we have to increase the SBC by 20% for the foundation design. Okay. So all these are the now permeability of the building. Permeability means how much opening it has. So that defines the permeability of the structure. So it is defined. So we have to calculate the percentage of opening. So this percentage of opening will be used to get the internal pressure coefficient in the structure. So we'll see that later on. So first we will calculate the area of cladding. So area of cladding will be this 9 meter into 30 meter into 2. So this 9 meter is what? Height. So height into total length. So this will give us the total area of the cladding on one longitudinal elevation into 2 for the 2 elevations, right? So it will be So this is our structure. I'm just showing you plan. So this is one face, this is other face. So this length is 30 meter, this width is 12 meter, and height is 9 meter. So 9 meter height into this 30 meter length into 2 for one for this face, one for this face. So it becomes 2. Then 9 into 12 into 2. Similarly for these two faces. 9 is the height, 12 is the width, and 2 are the faces. Plus 0.5 into 12 into 1.5. This is for the roof. So for roof, it will be like this, right? It will have some slope like this. So we have just calculated the area of this portion, total area. So this gives us the total area of cladding. Now we have to calculate the total openings. How many openings are there? So these details, opening details, you can get it from the architectural drawing. In architectural drawing, all the sizes are mentioned. What size of window is, what is the height of the doors, if there are any exhaust or any shutter. So everything is there in the architectural drawing. So you, to get the area of openings, you have to refer to the architectural drawings. Then from that we will get the total area of the opening. So window we consider 14 numbers, total 1.2 by 1.2, so 20.2 meter square is the total opening of the windows. Rolling shutter 12.92. So total opening or total area of opening in the shade is 33.08 meter square. So we just need to calculate the permeability. So how much percentage it is? It is coming around 4.27%, which is less than 5%. So building, we can say that it is a low permeable building. So there will not be a much internal pressure development. So based on this, we got the internal pressure. So where the cladding permit flow of air with openings not more than 5% of the wall area, but where there is no large opening, it is necessary to consider the possibility of internal pressure coefficient to be 0.2. So this is given by the code. So buildings with medium and large openings. Building with medium and large opening may also exhibit either positive or negative internal pressure depending upon the direction of wind. Building with medium opening between about 5 to 20%. So the percentage what we have calculated is this percent. That is percentage of the opening. If it is between 5 to 20% of the wall area shall be examined for the internal pressure coefficient of 0.5 and later with the internal pressure coefficient of minus 0.5. So we are considering, first time we are considering compression, another time we are considering suction, and analysis which produces greater distress of the members shall be adopted. So first we will analyze building with by considering the internal pressure coefficient of plus 0.5, and in other case we will consider the minus 0.5. And the worst result, whichever combination is providing worst result, that will be considered for the design. When the percentage is larger than 20%, when the opening percentage is greater than 20%, in that case the internal pressure coefficient will be 0.7. Okay, so since it is less than 0.5, it is less than 5%. In that case, we have to consider the internal pressure coefficient as 0.2. So in the case of building where the cladding permits the flow of air with the openings not more than about 5% of the wall area, but where there are no large opening, it is necessary to consider the possibility of internal pressure being positive or negative. Two design conditions shall be examined, one with the internal pressure coefficient of plus 0.2 and another will be minus 0.2. So in our case, we are just below the 5%. That's why we have considered the internal pressure coefficient of 0.5. So are you getting this, all those things?
Yes, sir.
Okay. So now we got the internal pressure coefficient, but we have to get the most important is external pressure coefficient. So whenever there is so will it be there, will there be any internal pressure coefficient if the structure is closed, structure is open? If structure is open, will there be any internal pressure coefficient? What do you think? Can you imagine what happening actually when we consider the closed structure? For open structure, will there be any internal pressure coefficient? For open structure, there will be no internal pressure coefficient. There will be only external pressure coefficient. So internal pressure gets developed due to the openings present in the wall. So you must have experienced when if there is any opening or window in your home, and if wind is flowing through this, then when you stand just in front of the window, you will have so much of wind feel, right? But as you just go on other side of window, you will not have that much of wind pressure, right? So whenever opening is there or small opening is there, the wind will flow through that and it will create a pressure inside. So that is internal pressure. And external pressure is like directly applied on the surface. So we will just calculate the internal pressure, how it is. So just to get that external pressure coefficient, what we need, roof angle, it is 14 degree, then height to width ratio and length to width ratio. So as per code, we have different pressure coefficient, different external pressure coefficients, and for different type of arrangement. So these are the force coefficient for the wall surface. These are for the roof. These are for the monoslope roof. If you have a slope on only one side, then this force coefficient we have to use. So first we will see for the wall how we can get the force coefficients for the wall. So here, as per code, they have given some criteria like height to width ratio if it is less than 0.5, and length to width ratio if it is less than 1 or greater than 1 but less than 1.5. Similarly, greater than 1.5 but less than 4. So based on this condition, we have to select the uh, force coefficient for the external pressure. So in our case, height to width ratio is 0.75. So where we are following, so we are falling in this category. We are greater than 0.5 but less than 1.5 because our h by w ratio is, height to width ratio is 0.75. Similarly, length to width ratio, it is 2.5. So length to width ratio, it is 2.5. It means it is more than 1.5 but less than 4. So we are falling in this category. So we are falling in this category where the coefficients for 0 degree 0.7, 0.3, 0.7, 0.7, and for 90 degree minus 0.5, minus 0.5, plus 0.7, minus 0.1. So what are these coefficients? So if you see, this A, B, C, D are the surface where on which the force or wind pressure is acting. So we have four surface, right? For any rectangular building, we will have four surface A, B, C, D. So when we are considering wind at 0 degree, so this angle, if it is 0 degree, then wind will act in horizontal direction. So in that case, A is the face, which is windward face. B is the leeward face. We call it as a leeward face. C and D are the side face. So the face on which wind is acting, it is called windward face because it is in the direction of wind. So here this A, B, C, D. So A, so this will be the force coefficient for this surface, it is 0.7. For B, it is 0.3. For C and D, these are the minus 0.7, minus 0.7. So now can anyone tell me what this plus and minus sign denotes?
So direction.
Yeah, it is showing direction, but what is actually happening here? When we are saying direction, if it is 0.7 acting in this direction, so load is acting in this direction, but still why we are showing it a negative? And what will be the direction? I'll just draw two sketches. Just let me know which one is correct. If we are considering the directions based on those convention, sign convention, I'll just draw one sketch. So this is building. This is one load. This is other load. These are the loads on the side face. So here we have 0.7. Here we have minus 0.3. Here we have minus 0.7. Here also minus 0.7. Okay, one is this one. Another will be. So this is the wind direction. This is plus 7.7. So this is minus 0.3. This is again minus 0.7. And this is also minus 0.7. So which one is correct? If I just remember this one and this two. So which one is correct? First or second?
First one.
First one. Okay. So in first one we are showing this direction of wind. It is away from the wall, right? So what it is creating? It is creating tension in the wall or suction in the wall. That's why it is given as a coefficient of minus 0.3. So whenever this wind will blow in this direction, what will happen? The wind will go like this and it will create suction over here, right? So this portion will have pull out force, like pulling effect it will have. That's why it is given as a minus 0.3. Correct? Similarly for these side faces also. Okay, so that's why it is shown as minus 0.7. So in STAD or wherever you are applying load, you just need to consider this sign convention to apply the loads. Okay, so we got the force coefficients for 0 degree, 90 degree, right? So these are the force coefficient for 0 degree, 90 degree, and CPI is internal pressure coefficient is plus 0.2 minus 0.2. We have to consider. So based on this, we have to create a load combinations or some cases where in which we are considering for 0 degree plus means CPE plus CPI and CPE minus CPI. So that will give us the two combinations. And worst of that, we have to consider for the deciding the section size. Okay, so I'll just show you. So these are the some calculations I have prepared. I have prepared some simple sketches, so it will be easier to understand. So first case is CP plus CPI, external pressure coefficient plus internal pressure coefficient. So this is the phase A, B, C, D. We are considering wind at 0 degree. Wind at 0 degree. So this will become my windward phase. This will become my leeward phase, and these two are the side phase. So for A, the factor is force coefficient is 0.7. For B, it is minus 0.3. For C and D, it is minus 0.7. Okay, so these we have wrote all the force coefficients, external pressure coefficients, then plus CPI. So we have to add this 0.2. So when we are considering plus, it means that it is acting on the wall, right? Earlier we have seen this. When it is minus, it is acting away from the wall. But when it is plus, it is considered as acting on the wall. So here we are considering plus CPI. So 4.2 shall act on the wall. So we have shown the direction of the load. It is acting away. It is acting on the wall. So we just need to make algebraic sum of these two coefficients to get the net pressure coefficient on the surface. So for A surface, it is 0.7. It is acting on the wall, whereas this 0.2, it is, since this is internal pressure coefficient, so it is balancing this external pressure coefficient. So the net pressure is 0.5, and it is acting on the wall. Similarly for B, it is this pressure, this force is acting away from the wall, and this is acting on the wall, but it is additive. So internal pressure is, so in this case, for this wall, internal pressure is also pushing the wall away from the structure. So that's why it will be additive to this 0.3 plus 0.2, it will be a 0.5. For these two faces, 0.7 plus 0.2, because these both are in the same direction. 0.7 plus 0.2, 0.9. Here also 0.7 plus 0.2, 0.9. Okay, so this is first case where we have done CPE plus CPI. In second case, we just need to reverse the sign of CPI. So CPE will remain same, but internal pressure coefficient we are considering suction. So this will create a suction inside the house or inside the building. So in that case, the resultant coefficients are 0.7 plus 0.2, because direction is same as that of external pressure coefficient. So we got 0.9. Here 0.3 minus 0.2. So it will be a 0.1. Net factor remain is 0.1. In this case, 0.7 minus 0.2, it will be a 0.5. Similarly for this phase, it will be a 0.5. So we got two cases, CPE plus CPI, CPE minus CPI. So clear this one? These two cases are clear?
Yes, sir.
So we'll go to the third case. So for this case, you can prepare total 8 combinations. So based on these two cases, in other case, you can just reverse the windward phase. So first we have considered windward phase, this one. In other combinations, in third combination, you can consider windward phase, this. But there is no need to prepare all the 8 combinations, because whenever we design any structure to keep the symmetry, we provide normally same section sizes instead of having different section sizes. So we can limit the number of cases based on this criteria. Okay, so third case will be for the 90-degree wind load. So when the wind load is acting in 90 degree, in that case our windward phase will change, right? So earlier this was the windward phase, now this will become windward phase. So whatever, so for factor C, the 0.7 will be the external pressure coefficient. For D, it is minus 0.1. So it is again creating the section C. load is acting in this direction, and here it is also creating a section, so it is minus 0.1, and these two become, A and B will become the side surface, and those are having coefficient of 0.5, 0.5. So again we will consider the CPE plus CPI. So 0.2 will be the internal pressure coefficient, and with the algebraic sum of all these coefficients, we got the net resultant 0.7, 0.7 on the side face, and 0.5 on windward face, and 0.3 on the leeward face. Same combination with the internal pressure coefficient, which is creating the suction. So 0.7, same algebraic sum will be done, and we got the 0.9, 0.1, 0.3, 0.3. So from all these cases, what we can see that, so when the wind load is acting in 0 degree, so this phase is getting designed for this case 2, right? And when the load is acting in 90 degree, then these two phases, for in case 2, this portion is got designed. In case 3, this surface is having maximum coefficient. In case 4, this surface is having maximum coefficient, and in other case, so in case 1, it is both the side faces or this top surface are getting designed. So different cases are governing for different surfaces. So based on that, we have to provide the section size which will be sufficient to take load due to all the cases. So this is how we just calculate the total force coefficient. Then we have to divide this force, or we have to apply the total wind load on these columns, steel columns, so based on their contributory width. Okay. So first thing is, for wind load on columns, our span is 5 meter between column center to center, and 6 meter on the gable end columns. So for calculation, wind load on column A7, A1, A2, and A6. A7 means this column, then A1 this column, A2, so this is for the windward face. For windward face, end column is A7 and A1, these two columns. For that, contributory width will be the half of the spacing between the column, that is 5 by 2. 0.5 is the force coefficient for face A, and 0.706 is the design wind pressure, right? So 0.5 is the force coefficient into design wind pressure into the contributory width. So we got the 0.8825 kN per meter will be the load acting on these two columns for its complete height. For intermediate column, it will be 0.5 will be the force coefficient, 0.706 will be the design wind pressure, and 5 will be the contributory width. So it is 1.7625. So for this phase, we got the total wind load. For leeward phase, similarly, for corner columns, there will be a half contributory width, and for interior columns, it will be a full length of the, or full span we have to consider for the load. It is minus 0.5, so it will be a minus sign here, and the force will be 0.88, 1.76. Similarly, in the transverse direction or in the on side faces, we have calculated the load. 0.9 is the force coefficient, 0.706 design wind speed, and 6 by 2. This is the for corner column. For this column and this column, it will be a 6 by 2. That is half contributory width. And for B1 and B7, so for this grid, the central grid on both the gable ends, it will have a contributory width of 6 meters. So based on this, we got the total load of 1.9 and 3.81. So similarly, for all these 4 cases, we have just worked out. So this is for the case 1. It is I have calculated here in detail. For case 2, I just wrote the values. and wrote the net pressure. So for each column, this single column indicates the or intermediate columns. These are the corner columns, and we got forces for case 2, case 3, and case 4. So this is how we got the total wind load acting on the flat surface of the shed or wall of the shed. Okay, so up to this, any queries? Any queries on this?
सर ये विंड लोड और कॉलम फिर से समझा, नहीं समझ में आया।
कौन सा
सर ये मेरा कहने का मतलब सर, कॉलम पर जो लोड लगेगा विंड लोड,
हाँ,
तो वो एक ही तरह का लोड लगेगा ना सर? ये डिफरेंट टाइप का लोड है, 158 किलो न्यूटन, 9 किलो न्यूटन।
ये एक means this 1.58 kilonewton per meter, this will act on the corner column only, and this 3.17 will act on the intermediate columns. It may be 3 columns, 4 columns, 4 columns, all will have the same load.
तो सर इसका डिस्टेंस सेम रहेगा तो सेम लोड लगेगा? जैसे एक कॉलम से डिस्टेंस दूसरे कॉलम डिस्टेंस सेम रहेगा ना सर?
सेम रहेगा तो ये लोड लगेगा. अगर if span is different, say let's say if you have a column at 5 meter and next column is at 6 or 8 meter, then accordingly you have to calculate the contributory width. It will be half of the span, and based on that you can get the load here.
तो सॉफ्टवेयर भी इसी तरह डालना पड़ेगा सर?
क्या
सॉफ्टवेयर के अंदर जो इनपुट करेंगे लोड, तो इसी तरह मतलब डिस्टेंस कैलकुलेशन करके फिर इंटर करना होगा उसके अंदर?
Yes. For closed structure you have to enter like this only. For open structure you can generate load in the STAD itself. You don't need to calculate all these things. If you are applying load for the closed structure, then you have to calculate like this only. For open structure you can generate the wind load command in the STAD, and it will automatically consider the load based on the section sizes provided.
ओके सर, देखता हूँ फिर से दोबारा रिवाइज करूँ फिर बात.
Okay. So the next will be the wind load on the roof. It will take some time. So instead of today, we'll see this in the next session, so that you will come to know. So you can go through this video. This video will be shared in the I think teaching room or in somewhere in the group. So you can go through this video once again, and if you have any doubts, then you can get it clear in the next session.
सर ये आप ये पेन से जो लिखे हैं उसको सेंड कर दीजिएगा, और DVR भी सर, दोनों.
I'll ask the host to send these documents because I don't have access. They might share all these in the respective groups.
ओके सर.
Yeah. Okay, so just let me know if you have any doubts so that we can clear it now, and then in next session we'll see the wind load on the roof.
सर सर हे कोडचं 2015चं पण एक वर्जन आलंय ना आता, ते आपण यूज नाही करत का आता?
यूज करतो, बट मोस्ट ऑफ द टाइम बऱ्याच वेळेस जे लोकल कन्सल्टंट आहेत ते जुना कोडच यूज करतात. 2015 पण आहे, बट माझ्याकडे आता नाही येतो, सो मी त्यामुळे तो ओपन नाही केला. बट मेथड मोर ऑर लेस विल बी द सेम. It will not change drastically. That only thing is that there might be a change in some factors like importance factor, like probability factor or importance factor might be changed based on the study, or some additions like some clauses or SBC clauses, those are added. I just need to check 2015. I'll just go through that. I'll see how much difference is there, but I'm sure it will not be any major change, because this method is there in the American code as well. Even if you are using American code for the wind calculation, it has the same method what we are just discussing. So method will be the same, only there could be a change in the factors only, but calculation method will be same.
Okay, sir.
If anyone of you have that 2015 code, can anyone share on WhatsApp or anywhere so that I can go through that?
सर क्लासरूम के अंदर स्टील का कोड सारा भेजा हुआ है सर.
In what?
क्लास हाँ क्लासरूम हम लोग का एक ग्रुप है, मेल किए मैम, तो उस पर स्टील का रिलेटेड जो भी कोड है वो उसमें मेंशन दिया हुआ है, मैंने खुद देखा है.
अच्छा, okay.
हाँ.
No, I don't have access to that classroom, so maybe I need to ask them to send it to me after downloading. Okay, I'll check with them. I'll just see to get it downloaded for me. Okay, so if you have any doubts, we can have it in next session also. And then we'll see the wind load on the roof.
Okay sir.
Yeah, okay. Okay, so we'll stop here today, and next session might be on Saturday.
I think sir Monday, Saturday and Sunday David class है.
Okay, okay.
Maybe.
Okay, okay. So, okay, no issues. Accordingly, it will be informed in the group. So,
Okay sir.
whenever it will be there, we'll have the next topic. Okay.
Okay sir.
Okay. See you. Good night all.
Good night sir.
Good night, sir. Good night.
Thank you, sir.